So I am so pumped that we have Steve Beresford joining us today. Steve has worked along the academic industry interface for over 25 years. His industry involvement has included previously serving as a Chief Geo for IGO, First Quantum and MMG, while his academic involvement includes currently being an adjunct professor at the Centre of Exploration Targeting at UWA, and previously a professor at UWA and a lecturer at Monash. So Steve has been on the board of several private and public companies and was once fortunate to be part of WMC. He's the co-author of the Uncover Roadmap and Australia's National Decadal Plan for Geosciences, and is currently the chairman of the industry board at the CET and co-host of the Exploration Radio podcast. So with his vast expertise, I'm really excited to hear from him today about camouflaging a supergiant, magma salt interaction, and polymetallic nickel copper deposits. So it is going to be a great session. I hope you all enjoy it. Please use the chat. We'll open up the floor and have some discussions at the end. And yes, thank you so much, Steve, for joining. It's just wonderful having you.
Thanks very much, Jess. Just a wee apology for last week. For anyone who expected to see me last week, I had COVID, unfortunately, and wasn't really in a state to present. So today I want to talk about nickel copper systems and a little bit of an obsession I had. If anyone's heard me speak before, this is a topic I've been on for a good year or so now. And this is a different talk. I always give a different talk every time, but it's still the same flavor, which is around something I think we're not doing in the world of exploration and something I'm doing. So I want to start all my talks with something just a little bit different, and I want everybody to focus on these staring eyes staring back at you. This is the White Temple from Uruk in Mesopotamia, on the banks of Tigris and the Euphrates. And this is nearly 7,500-year-old statue. And the piercing blue eyes are made of lapis lazuli, which is going to be a theme at the beginning of this talk. This is from a period of time when writing was first coming along, and the world starts to become connected through the civilizations of the Sumerians, the Akkadians, and then the Egyptians further to the south. And lapis lazuli has a role to play in this part of history, as I hope to show you. So the Epic of Gilgamesh, which is on the left there, is in cuneiform. And I've been fortunate to read this story. This is the first ever piece of literature, or our oldest known piece of literature, written on lapis lazuli. It's a story from pre-Odyssey, pre-Homer, and the Iliad, if you like. The other thing that's important on the bottom left is me and my daughter got a chance to see. That's Tutankhamun's death mask, and that's made of lapis lazuli. The 10 Commandments, if they're real, are assumed to be written on lapis lazuli, and certainly the Bible documents lapis lazuli in a number of places. The other famous document is the Book of the Dead. Here in papyrus form, the Book of the Dead is written also on lapis lazuli. More significantly, for younger examples, Michelangelo's the Sistine Chapel, and actually every painting since the Renaissance till 1834 is in lapis lazuli, using lapis lazuli as a pigment. Not until 1834 have we been able to document or duplicate that particular blue color, that very amazing blue color you can see in the Fabergé egg from the Russians. And then just to keep this story really going, even Martin Luther and the beginning of the Reformation is written, the 95 Theses are written in lapis lazuli ink as well. So a number of moments in history that really draw together over 10,000 years of history about lapis lazuli. And lapis lazuli is going to be my cornerstone of the arc of the story that I want to tell you today as relates to nickel sulfides. So what is lapis lazuli? Its main component is lazurite. Lazurite is a sodalite mineral. It's derived, the word comes from the core word lalivard or lazulum. Some of you will recognize that it has the same root word of azurite, the copper carbonate that we know so well in geology. But in this case, instead of copper, the blue chromophore is sulfur that we're talking about. So the blue coloration that beautiful ultramarine blue color comes from sulfur 3 in particular. Now, the really unique thing about sulfate, or about lazurite, is that it's a sulfate, a sulfide, a halide, and a clathrate mineral. And that in itself is pretty fantastic. For those of you who know your fundamentals of nickel sulfide geology, 3 of the main ingredients to form a nickel sulfide are caught up in the sulfate, sulfide, and clathrates. So we're talking about really unusual mineralogy, unusual chemistry, but very much the chemistry, the 3 elements that we need to form a nickel sulfide system. The mineral sodalite is a feldspathoid, not a common mineral for most nickel sulfide systems. So what is lazurite? What is lapis lazuli? It's quite commonly known as a contact metamorphosed dolomite in some skarn systems, but it's actually largely a metamorphosed evaporite system, what we would call a meta-evaporite. So what's a meta-evaporite? A meta-evaporite is where the soluble components, i.e. 99.9%, is removed, and the insoluble components that are left behind during metamorphosed are the meta-evaporite. So I'm going to talk about a lot more minerals and a lot more than lazurite. But lazurite is the cool mineral to open the show, if you like. And we'll come back a little bit later on and we'll talk about other metamorphosed evaporite indicators. Now, this story, the reason I started at Uruk in Mesopotamia is there is an ancient part of the Silk Road that's known as the Lapis Road, named after lapis lazuli, that actually connects Central Asia with Constantinople. And that road is being rebuilt, connected as part of the Belt and Road Initiative, as part of the Silk Road. It connects Xinjiang or China with Europe. And that's a massive initiative to reconnect Central Asia through the Stans and through Turkey to Istanbul. And the really key thing about the Lapis Road is that it's more than a road. It's actually a series of geological provinces, and it hosts the world's biggest Phanerozoic large igneous provinces, LIPS. It hosts the large salt belts of the world, and it hosts, not surprisingly, nickel sulfides. And so this story is going to start in the Lapis Road. And if I get this right, by the time I finish here, we'll end up talking and finishing back in the Lapis Road. So what do we know about lapis lazuli or lazurite? Actually, most of our scientific understanding of salt skarns comes from Pliny the Elder at the beginning and from the volcano, the Vesuvius. Now, I'll finish with the history lesson in a minute, but Pliny the Elder is the first person to write about the mineral lapis lazuli in his book, The Natural History. And he's actually dies in the Vesuvius AD 79 eruption. And many of you will probably know that he's the first scientist to actually document the AD 79 eruption that destroys Pompeii and Herculaneum. And rather ironically, that deposit actually contains lithics, blocks of lapis lazuli in the eruption products. And the picture you're looking at here in the right example is in fact a lapis lazuli block, mostly a metacarbonate, sitting in the fall deposit from the AD 79 eruption. It's a coincidence that the man who first describes it ends up being pummeled by the same mineral in Pompeii. Now, what we mostly know doesn't just come from Vesuvius, it comes from the other famous Italian example, Italian volcanoes, Collo Albani. So Vesuvius is in Naples, Collo Albani is in Rome. These are both volcanoes where the magma systems are developed inside salt and calc-silicates. And so we know a great deal about the igneous petrology and the metamorphic petrology from these two volcanoes. Now, when most people think of evaporites, meta-evaporites, they think of something that looks a little bit more like this, and rather than what I'm going to spend most of my time talking about. So a lovely bedded, beautiful range of hydrous and anhydrous salt sequences. But in fact, the vast majority of salt evaporite sequence in the rock record look more like this. Now, this is a Google Earth image rather than showing you a rock photo, because I've never been here. This is Afghanistan. itself. And this is the Sarasang Valley. And this is the location of Lajawad, which, if you remember, is the Persian word for lapis lazuli. And what I really want to focus on amongst those 4,500, 5,000 meter peaks is two white strips that you can see here in the pointer, which are two silicate zones. This are the calc silicates that host the lapis lazuli, that host the world-class Sarasang mine. In fact, Sarasang is just up the valley from here. This is where most of the world's lapis lazuli comes from. And my real point is just to point out that this is actually a well-preserved example. Now, what's missing from this sequence? 99% plus of the rock mass has been removed. That's what evaporites happens to evaporites in the rock record. If you happen to live in younger sequences or well-preserved sequences, you may not be aware, but the vast majority of the evaporite rock sequence is removed from the rock record. That is its characteristic, highly soluble material. Now, this is not a talk about evaporites, but the perspective I'm talking about today is how do we go from meta-evaporites to these systems. This is taken from Nova, but it's the same point, which is we're going to turn a salty rock sequence that we want to interact with into 100% sulfide. And this is quite a photo. Nova might be a relatively small system, but very much the point of my talk is going to be to talk about how to turn it into supergiants through salt interaction. So I'll give you the take-home messages right now so you can sit back. But what I really want to talk about is the largest and most valuable deposits, nickel deposits, actually have copper and PGs, not as credits, but as equal components. And they're formed by magma salt interaction. That's the key process that we want to involve. And these systems all take place underneath in the volcanic systems of what we call halo volcanoes. And now not everyone is familiar with the term halo volcano, but the word halo here stands for salt. So these are salt volcanoes. And I'll give you some examples of what salt volcanoes look like in a moment. But we're very much going to be talking about magma salt interaction, or this fancier halo volcanic term. Now, the most for relevance today is not going to talk about genetic processes. I'm going to be way more pragmatic than that. And I want to talk about something that I think is eminently practical, which is just how to change the deposit footprint of nickel sulfide systems, how to make them more salient than, for example, electromagnetic techniques, which is the dominant techniques we use. And the real key to my logic is that when we see these footprints, this ultra high temperature halo, which is what UHT stands for, not milk, when we see these things in white rocks, then we get extremely obvious salient footprints. If any of you work in porphyry systems, this is like the opposite logic. So if any of you worked in porphyries, if you look for a porphyry, a potassic zone, or a green rock zone in white rocks, like quartzites or carbonates, then the footprint is less salient and less obvious than it is in volcanics. It's actually the opposite in nickel sulfide systems. It's way, way more obvious, way more salient in white rock systems, not just carbonates, but very, very specifically in evaporites themselves. So I'm going to be talking about changing how we view the emplacement footprint, and I'm going to put aside the genetic discussion for just a little bit. It's a discussion I'm prepared to have, but this one is a very simple, straightforward premise, way more obvious if we look for white rock footprints. Key problem, these white rock footprints are harder to find. And that's because salt doesn't just so much as preserve poorly, but as vanish in the rock record. There are very few things that vanish in the rock record, and salt is one of them. And I'll take you through that process. So the signature we're looking for is somewhat cryptic. The deposits themselves, I think is a good term, are somewhat camouflaged. Now, for those that are intimidated by this, I choose to be optimistic. We're going to develop techniques, new remote sensing, hydrogeochemical and mineralogical techniques, so that we don't overlap and overlook these camouflage techniques that look like other things. So cryptic doesn't have to be bad if we use new approaches. So this is my view of the nickel copper PG pyramid, really looking at classifying nickel copper PG systems. Now, all nickel copper systems, nickel copper PG systems, have these three elements in different proportions. And we tend to talk about the end members, nickel PG systems, and the lesser known magmatic copper systems as discrete deposit types. But in fact, very much of what I'm talking about today are not nickel systems with PG credits or copper credits, but systems that sit squarely in the middle. And I've mentioned this in previous talks. I call them the polymetallic systems. It's certainly not semantics. It's absolutely of fundamental economics. Norilsk is the fourth largest copper deposit in the world and the second largest nickel deposit. It's not irrelevant that they have those two metals as credits. It's what makes polymetallic systems the best deposit style of any in terms of economics. So you might want your deposit to fit onto the middle of this graph, but it's a very specific story that I'm trying to give today about a subtype of deposit, a polymetallic systems. Now, this is a graph I've shown before, and the reason I don't update it is because I don't have the data. But Richard Shodney and I did this work 10 years ago, where we showed that nickel sulfide systems were in fairly serious decline in terms of discovery rates. And one of the things that people quite often mention is, but since then, Steve, things have gone very well, haven't they? And in fact, things haven't gone very well. And so I want to start by showing just how poor the last 2 decades have been in terms of discovery. Yes, we've seen the discovery of the Flat Reef, Sakati and Nova in 2013, and Julimar is a great discovery here in Western Australia. But they are the dominant things I get to add to this particular graph. So I'll come and show this in a bit more detail in a minute, but discovery rates are not just in decline, they're almost flatlining. And I really want to have the conversation as to why. So let's look at one detail. There's a lot on this graph to take you through at another point, which is the discovery of Pechenga. And I just used it because I always use other examples. And what I want to show you is, as with time, and there's 2 world wars to complicate this story of the discovery of Pechenga, as we move through time, there's a large amount of time on this axis. There are 2 world wars to complicate the story. But what we'll see as we move from the shallow prospecting phase, that's the discovery of Koala and Kotsulvara, the big system of Pilgiavi gets discovered early, that's the second ore body. But the deep high-grade systems of Sapolani and the Sputnik systems were really only found as a direct result of the Koala deep drill hole system. And these systems happen many tens of decades after. And that's something I want to come up in discussion later on when we start talking about how short-term focused we are in nickel sulfides and just how these systems have evolved. And I could put Norilsk up here, I could put Nova, I could put Thompson or any system. So let's look at those last 20 years. Now, the first thing I'm going to do is jump to the previous 10 years, because 82 new nickel sulfides were discovered around the world between 2002 and 2012. Now, people might go, why are you choosing arbitrary dates? They're not really arbitrary. I'm choosing 10 years ago from today and 20 years ago from today. So hence why I'm not choosing round decade numbers. But you can see a number of discoveries across the world there. Green refers to green fields, brown is brown fields, and khaki is that I would prefer to call them brown, but I know I offend people when I describe some of these systems as brown fields, but to me they're brown fields, and I'm the one giving the talk, so I'm the one who gets to classify things the way I want. We can take that offline and do that some other way. The point is, in production of the things in red, what we can see is 82 prospects. Looks like a fairly good run, but this was a nickel boom. Nickel hit $53,000 a ton, and I'll point out that there are 0 world-class discoveries in that particular decade. So that sounds like an okay story, perhaps not ideal, until we get to the next decade and the last decade. And this is quite a hard story to accept. Even if you're optimistic, there's very little on this figure at all. It's an awful decade, and there are many reasons and to explain as to why we've had such a poor. And in fact, the reason why WA's had such a strong decade is because of the discovery of Nova in the previous decade. is actually sustained nickel exploration here in WA, but the world has very little to show, and of course, no other world-class discoveries. And here's an interesting point. Every discovery has been made by a junior in that decade. So unbelievably, we need to really focus on this past and ask a few serious questions. What has happened in nickel sulfides? Many of you know that we were in a downturn in some of that period of time, and nickel in particular was hit very hard from the previous decade. But nonetheless, people like myself have been a nickel explorer the whole way through. So let's talk about that story. A common lens of belief that I get is that nickel is too hard. It's too hard to find. But that's the worst decade since before World War I, and depending on how you do the stats, since 1897. That's quite a statistic we're facing over a 100-year period. We continue to explore for them in the same manner we have over that period of time, and we seem to be expecting a change in fortune. There have been some successes. Nova and Julimar really notably have been successes in new belts, I might add, and that's a point I'll come back to. But my point is I'm prepared to do something different. And so I want to take you through this salt story, this meta salt story, as a key ingredient in the genesis of giant systems. And just ask a couple of questions that I don't expect me to be able to answer, but what if these things are more common than people think? What if preservation is way more of an issue than people want? What if the footprint is more salient if we could lower false positives? What if it's easier than we think? So one of my explanations, and this is to see the discussion that comes afterwards, is to say something like, well, one of the things that I really obviously know from working in this industry is we're mixing up exploration strategies from other deposit styles. And this one in particular, I think, is a fatal flaw, and that's porphyries. So porphyries, example on the left is the Andean porphyry belt, 65 discoveries, 65 mines, 600 million copper tons spread over thousands of kilometers. The same figure on the right is the world's largest nickel belt at the same scale. And what you'll notice is there are two deposits. So the first thing you should notice is there is completely different clustering relationships for the deposits. Absolutely different dynamics in terms of how you are the first follower versus the second follower versus the 100th follower in terms of the relationship in nickel. Every nickel geologist knows this. Second follower is first loser in the world of nickel sulfides, but that's not the case in porphyry systems. Now, that's history, but it's also technical geology. It's a technical fact that these systems cluster different. Here's the next one. We know where most of the world's arcs are, but a new province the size of the Andean province is found every decade. In fact, in some decades, we find more than one every decade. Now, if there are porphyry explorers in the room listening, imagine if I could tell you that I could find an Andean province, a new one to explore every 10 years. You'd be horrified at the scale of that opportunity. And I am horrified that that simple premise isn't public knowledge, that we can find something like the Andean porphyry belt. It is an incredible difference between the deposit styles. We can't treat them in the same way as porphyries. So here's my cartoon that I borrowed to explain this. Second mover strategies work, but they really assume that we've landed on the dung in the first place. And it's just simply not true when it comes to nickel sulfide systems. Different strategies for different deposits. The current strategies we dominantly have no basis in history, no basis in economics, and no basis in technical clustering characteristics. And I've never met a nickel geologist who believes we're doing it right. So I want to ask a question, which is, why are we not standing up for ourselves? Who's telling us that we're to explore in the ways we've been exploring? It sure as hell isn't me, and it isn't a nickel geologist that I've met either, but somehow we still are. So those are big, bold words to get everyone fired up for questions. So one of the things that I've been very fortunate is that people have allowed, and I've been allowed to work all over the world. And this map is full of pretty pictures, pretty dots of where I worked. And one of the things I really hope is that my own particular adventures can contribute to some form of change. The breadth, obviously, rather than depth of knowledge that can provide some new angle or contribute in some way to a new angle. So just in terms of salt, there are two things you can do genetically with evaporites that are important to nickel sulfides. One is salt is a seal in terms of magma emplacement, in terms of basins. It provides a threshold barrier that dams and prevents magma from reaching throughout the whole system, and it focuses magma flow. It also drives sulfur saturation, and we can think of nickel sulfides much like porphyries, is that we need to release the system from one reservoir to somewhere else. And what is that trigger that enables that release is very much the whole point of mineral systems thinking. But I don't actually want to talk about that part of the mineral system. I want to focus on salt as a footprint host, specifically for this analogy that I've already made with porphyries, the opposite of porphyries, that I just want to make the footprint as obvious as possible. So I mentioned there's a trigger. One of the things that salt can do is we see a lot of overpressured intrusions, these small oxide breccia pipes that come through these things. These systems tell us that we're getting transient release of magmas. They're present across many nickel sulfide systems. So it's an argument we can go through in another day. What I really want to do is focus on this specific example, which is the primary footprint of nickel sulfides. Now, what you're looking at is a cross-section. I want everyone to focus on the green area. The green is the cross-section of the intrusion. The first and most important thing is the scale bar, to realize it's a tiny intrusion. It's one of these chonoliths that I talk about. It's coming in and out of the screen at you. I deliberately show it in cross-section to really exaggerate, or actually to really illustrate how small it is. Now, the massive sulfide, the EM detected contrast is in dark red there. And that's really the focus of what we're trying to find. But that's surrounded by an intrusion that has a very distinctive geometry. It's also just surrounded by exogenic sulfides that are often the country rock. But I really want to focus on the lighter blue color. The lighter blue color is the footprint generated by the emplacement of the intrusion in the sulfides. It's what we call the UHT, or pyrometamorphic alteration halo. It's the distal footprint. And I hope it's really clear that it's several times bigger than the intrusion itself. It's not the scale maybe of a porphyry, but given that we're talking about a magmatic, orthomagmatic ore system, it's a pretty significant observation that we can recognize a footprint at all. Now, this footprint is small when we're not in white rocks. It's only this size because it's interacting with salt or carbonates. So one way to look at the system is polymetallic systems open up new detection methods, because we're hybridizing a nickel sulfide system and how we traditionally look at it with skarn systems. Not just any old skarn, evaporites. So most skarns are formed by magma, and mostly intermediate to felsic magma, interacting with carbonates. In this case, we're talking about far higher temperature primary magmas, mafic magmas, not felsic magmas, interacting with evaporites. This is going to get way more complicated than your average felsic skarn system, but it's also going to provide unique footprints. And here's the real practical kicker for me. Not only is this figure here, this footprint, bigger than it is the size of the nickel sulfide deposit, it's in the hanging wall of the deposit. And therefore, we're finding it well before, at higher levels, stratigraphic levels, than the target intrusion and the target ore body. And this isn't just a theoretical point. This is how the discovery of Norilsk happened. We're drilling the hanging wall and recognizing the significance of the system. Now, many of you have probably worked in skarns, and there's nothing really unusual about the skarns in these systems. Here's my classification system, and it looks pretty similar to a lot of felsic skarn hosted systems. The big two differences here, I could probably contrast in the middle, is this is a classical calc-silicate skarn from Jinchuan. That's olivine in the middle of this system, whereas this is a sulfate skarn with anhydrite as the dominant skarn mineral here. So dominant calc-silicates with the normal minerals we might associate, and an evaporite skarn with a range of new alkalinities to deal with, new behaviors to deal with. Here's an example in the far bottom right, which really does explain the extreme variation. Here you're looking at shales intercalated with sulfate-bearing skarn systems. And the sulfate skarn is completely replaced and the shale is almost entirely intact. And that's pretty standard of selective skarns and other examples. But here's an example from a sulfate system or from an evaporite system. And these evaporite skarns are spectacular. I'm not going to get bored of showing you this photo. I show it in every talk I ever do. I think it's just so pretty. Having so much anhydrite in the skarn system just makes it look so dramatic. This is a perfect example of a skarn system in an evaporite. Here's a neat small example from San Francisco de Olivenza here, just showing you in purple the target intrusion overlain, in this case by a smaller exoskarn development with exogenic sulfides associated with it. We're dealing with mafic, ultramafic rocks, not felsic rocks, remember, way less common. Now, if we move to felsic skarn systems, many of you will recognize and know how to navigate these skarn systems in calcium, silica, magnesium space. And we're used to the minerals we might want to deal with here. Forsterite, that primary olivine or serpentine in the skarn, diopside, andradite, for example, in terms of garnets. But we're actually going to play over here as well inside the world of merwinites, lahnites, and spurites, minerals that are not so common, higher temperature in the calc-silicate world. Now, this is a figure I created to try and illustrate this. It's deliberately qualitative, but let me try and take you through it. Those of you who are familiar with skarns, you're off the axis to the bottom here. The top part of the axis, we've moved from felsic rocks to mafic to ultramafic rocks. And this is the distance from the host intrusions. And we're moving through the usual minerals, diopside and andradite, olivine, serpentine out to periclase. And now we're going to start adding minerals that are not so common. In particular, we might be familiar with the scapolites, primary scapolites, the suvenites, and the diagnostic mineral here, merwinites and lahnites. So lahnite is a calcium olivine. I don't know about you. I don't remember anybody telling me that olivine had a calcium member when I was at school. And all this process is taking place here inside halo volcanic systems. So magma interacts with salt. The salt is lost from the system, and here it is at the surface. This is Dalol in Ethiopia, and here we are at night. This is not my photo of salt flowing itself as a lava flow. These are absolutely spectacular systems where the salt is being removed from the system. No preservation potential, but what we do see is enormous restriction. So here's a cross-section just showing you the restricted nature of the system. What we see in terms of alteration, and this is epithermal in this case, is just so pretty. It's so extreme. And this is not something I'm referring to in terms of the alteration systems we're seeing, but just to illustrate the actual complexity of magma salt interaction here and what we're dealing with, both subsurface and in this case, in the surface examples. So I want to finish up by talking a little bit about how we go about recognizing this salt. If it's so important, but it's being removed from the rock record, we can't go around looking at systems that look like these beautiful evaporites. We can't use the traditional mineral systems or sedimentary basin systems here of trying to go through the stratigraphy and recognizing primary salts and trying to recognize where we would see nickel sulfide traps. But what we can do, and this is an example from the Siberian traps, is come back and try and use this approach to work out characteristics that we couldn't possibly have understood. So here's an example of my own work where the Oktябрьский and Karolak intrusion is hosted in the Radyshinsky Formation, which is an anhydrite-bearing sequence. And in fact, as the intrusion reaches the Mantorkovsky Formation, it turns into incredible salt peperites. And even though there is no hydrous salt remaining, we can infer the presence of hydrous salts in the rock record. That's a lay down simple example. Let me take you through something a little bit more extreme. So let's talk about preservation. Two things. One is the salt doesn't just disappear. We know that gypsums and halites struggle in the rock record, and hydrite can be preserved to high temperatures, but most of this material is flushed as soluble and is lost. So it's a bit like, and this is my analogy, trying to do archaeological record without organic material, which is of course what we do. Archaeology is entirely about trying to understand human history, and without human remains themselves, without the human component, which is preserved so poorly in the archaeological record. So erosional level preservation, they really, really matter. Erosional level itself is way more important than in porphyry systems. And for those of you who work in porphyries, you would know that it's already an important ingredient. We do have some ancient examples. We have 2 billion-year-old evaporites. This is some of my favorite work from a colleague of mine, Victor Malacek, and from Norway, a Russian man who's found these unbelievably beautiful examples in northwestern Russia. I'm very fortunate with working with him in northwestern Russia and finding things in the central Lapland greenstone belt that are 2 billion years old. But the really important part about this story is that these were found many decades after we hypothesized their presence in surface-based rock. They're only found in deep drilling. Now we've got plenty of examples in Australia in Neoproterozoic from the Officer Basin. Many of you will be aware we have salts preserved in the Central African copper belt as well. But the vast majority, very, very confident, large number of Precambrian evaporites are removed from the rock record. So we're only looking at relics of those systems. So most of what we see are what we call replacement evaporites or meta-evaporites. So no primary textures or limited primary textures. But we can see a variation between what we might call secondary minerals and tertiary evaporite minerals, all the way through to minerals that have nothing to do with evaporites at all. So what does this do to a volume? If you imagine if you're losing 99% of the mass, the reduction is huge. It's a good way to approximate that most of the volume reduction is close to 100% is removed from the rock mass. It's pretty extreme to talk about. So here's a beautiful example, Canadian example from the Stark Formation here of removing most of the characteristics of the salt, left with helikinetic textures. Helikinesis is the process of salt tectonics. And the only thing we're left with is carbonates, pelites, and silica as evidence that the rock, in fact, composed largely of salt. So here's one way to take that piece of logic, which is interacting with evaporites that are now metamorphosed is likely to be the most common exploration scenario we face. So far from something that's going to be rare, it's in fact going to be the most common exploration scenario we face for salt. Just because it's cryptic, therefore we need to be well and truly aware of it. So let's look at 4 scenarios to leave you with. Scenario 1, the deposit is hosted in carbonates, but the basin is known to be hosted in evaporites. Here's an example from Inkamati, where we know the basin is hosted in evaporites. We know the Bushveld is, for example. Here's an example from Siberia, where we know the Mantarovsky contains anhydrous salts like anhydrite, but we can see from the nature of the peperitic interaction that it must have contained gypsum and hydrous salts as well. This is a unique textural formation. We know that it's interacting with wet salts. Or this example, really common example where we see salt pseudomorphs, maybe hopper halites or gypsum here from the central Lapland greenstone belt or from Pechenga to nickel sulfide belts. We can infer they're present, but it takes decades for someone to prove. Now, these belts both have proved evaporites in them, but it's taken years after the discovery of these nickel deposits to prove it for some people. I think we can do better than that by inferring their presence a great deal earlier. And then I want to finish with the last scenario, scenario 4, with a metamorphic mineralogy only. This is by far the most common occurrence of evaporites in the rock record. Here's an example from Jinchuan, where the only thing we end up with is an intrusion and dolomitic marble. If I stand out from a distance in Google Earth here, I can see the intrusion, perfect outcrop, and Jinchuan intrusion sitting only in the Bajaswazi Formation, entirely in carbonate. As I get my eye in, I recognize I can see huge swaths of metacarbonates throughout this sequence as I move up into the Dunzigo Formation. But the Dunzigo Formation itself is made of silicified marble. It's amphibolite facies. Stromatolites are preserved. So I'm left asking a question that I am not going to answer, which is, what else can I do? Well, what I can do is I can look back through paleogeography. I can look for direct evidence from things like the Scotese Atlas, which we can now take back to 750 million years very accurately and all the way back to the beginning of the Mesoproterozoic, and understand the distribution of evaporites on the planet from facts. The next thing we can do is use paleoclimate modeling. Evaporites develop in what we call bilatitudinal zones. So if you have a look at the example on the right here, the green zones are inferred from climate models of where evaporites should have been developing during the Permian in this particular example. The actual examples and proof are in yellow, but the inferred evaporite belts are in green. So we can now be GIS enabled and predict where we should have had evaporites on the planet, even though the evaporites are no longer present. And of course, we can do this now back beyond 800, 900 million years now. So a large chunk of Earth's history, not just the recent past. So we can predict evaporites. We can map them in remote sensing techniques, as long as we take into account that we need more than just the calc-silicates. This is a belt that's nearly 100 kilometers wide, mapping calc-silicates, stunning outcrop. Of course, I wouldn't have shown, why would I show you a poor example when I can show you a perfect example? But mapping beautiful, easy to map evaporite sequences. I can combine anhydrite relics, but I can combine them with easily to use lithogeochemical techniques that enable me to map anhydrite presence, even when it's not present or I haven't done the detailed work to look at it. I can look at proxies. I can take a Scott Halley-like approach and look at the geology, the whole of Finland. And what I can do here is, even looking at alteration products, I can recognize belts like the Peripoja, the Kuusamo, and the central Lapland greenstone belt that are just lighting up as unusually albertized. Now, albertization here doesn't mean primary evaporites, but it is a proxy for high salinity brines, and in this particular case, derived from primary evaporites. I can map evaporites decades before I can prove it, that the evaporites even exist. But I don't even have to stop on theory of where I could look and large geochemistry. I can use minerals that are associated, minerals that I call salt-resistant indicator minerals. And for proprietary reasons, I can't show you a lot of this stuff, so I'll just keep teasing you with them. But it's a suite of minerals. And one of them I started the talk with. One of them is lapis lazuli. It's the most obvious mineral. It's a salt mineral. It's the thing that is left behind in the rock record. And here's the key, there is lots of this data. And so this is a pretty common thing. We all know we're doing it at the moment, generating databases, in this particular case, and using word associations, word semantics, keywords, huge geochemical databases of existing documents. Dark data was what the Cobalt Resources guys use it, of just existing data that isn't being used. And we can now do it in any language. I do this routinely in other languages using optical character recognition. Here's my mate Ahmed Salim's piece of software that enables me to put it in GIS and to recognize this in any report I want. I can do this non-searchable format. What's happening here? What we're doing is recognizing meta-evaporites on a hundreds-fold scale compared with what we had just a year ago. And it's so straightforward. And it means I can turn up somewhere like this, which is in North Queensland, and look at termite mounds. Not only do I have mineral chemistry, and then I can start moving into remote sensing and automated core logging that enables me to recognize minerals that are really common if you think through this particular lens. So to finish up, the vast majority of evaporites are not preserved or poorly preserved in the rock record. We've been talking about finding nickel deposits where the salts disappeared, but not the nickel deposit. So we're not talking about intruding metamorphosed nickel systems. And just the careful search for salt itself already is, I'm an active explorer, dramatically increasing the search space for world-class nickel sulfide systems. And yes, I started in the lapis road, but just let's take a look at the known evaporite belts of Australia. The first thing you can take from a talk that I mentioned today is these known evaporite belts are obviously not the only evaporites that we've got. So remember, evaporites are not preserved very well, and they're hidden in plain sight, both them and the deposits, because of this unusual characteristic. So it's been a very, very poor decade and poor 20 years for nickel exploration. I don't think we can keep on exploring like this. And so I think there's some strategic and tactical areas that I think we have got wrong that we need to start asking. And I want to seed the question by saying we've lost all the nickel-only companies, so we've lost collective knowledge. Maybe it's the loss and retirement of individual knowledge. I don't want to be answering that question. I have my own opinions, but I myself have moved on. I've decided to do something a little bit different because the stats suggest that we really need to. So I think I'll finish up there, Jessica, and open up for discussion and for debate. So thank you everyone for your time.
It was really thought-provoking. Thank you so much.